Hi, good afternoon, everybody. Thank you for showing up. So today I'm going to be talking about our work on coexistence of dedicated short-range communications and Wi-Fi. And this talk will focus on the implications of this coexistence scenario to the Wi-Fi system performance. So here's the outline of my presentation. So I'll be talking about the motivation of our work, some issues that can arise in this coexistence, and I'll describe the test bed that we had set up for conducting some experiments. And then we divide this coexistence analysis into two aspects. One is the impact of Wi-Fi on the DSRC devices and vice versa. And then in order to improve the Wi-Fi performance, we propose and implement an algorithm which we term as Real-time Channelization Algorithm, because that's what it does. And then evaluate its performance, and then I just give some remarks about what we've learned through studying about this coexistence problem. So DSRC it stands for Dedicated Short Range Communications, and it's a vehicular-to-vehicular communication standard which was designed for transmitting like safety-critical vehicle information. So, for example, you can communicate like lane change detection or such critical applications from one vehicle to another, so that you can prevent collisions on the road. And the spectrum band that's reserved for DSRC is in the 5.9 gigahertz band. Specifically, it's the 5.85 to 5.925 gigahertz band. So the 75 megahertz of spectrum has a 5 megahertz guard band, and then it has 7 channels of 10 megahertz each. So one of them is reserved for control information, whereas the others are used as service channels. So the physical and the MAC layer of DSRC is completely based on the IEEE 802.11p standard. So it's 802.11p, it comes from the 802.11 standard of a family of standards, and so a lot of aspects of the PHY layer and the MAC layer of the DSRC is similar to regular Wi-Fi, but there are some custom modifications that were done to make this standard suitable for high-speed vehicular communications. But DSRC hasn't been able to pick up so much. So the commercial vehicles still don't come equipped with the DSRC modules so that they can communicate with each other. So considering this underutilization of the spectrum, FCC in 2013 decided to consider allowing unlicensed devices to operate in this band. So specifically, it considered like Wi-Fi to operate in the DSRC band, and it opened up two chunks of frequencies in the 5 gigahertz band. Now, if you notice, the second frequency band, 5.85 to 5.925 gigahertz band, overlaps exactly with the band that's actually reserved for DSRC applications. So this creates a classic spectrum sharing problem where two technologies would share the same spectrum, and there are several issues that come up which I will be talking about throughout the talk. So of course, so since considering the safety critical nature of the applications for which DSRC was designed for, DSRC is the primary user of the channel. So every time a DSRC device is present, a Wi-Fi device cannot operate on that band, and of course, and that makes the Wi-Fi devices the secondary users of the channel. So before moving to the actual content of my presentation, I just want to give some brief details about IEEE 802.11ac, which is the latest Wi-Fi standard out there. So among the various enhancements that 802.11ac has brought in over its predecessors, channel bonding is one of them. So the objective is to increase the physical layer throughput. So channel bonding refers to bonding or like combining several channels in order to achieve a higher bandwidth channel. So the older 802.11 standards, what they did was they transmitted over a 20 megahertz channel always. So since more high data rate applications came up, there was a need for a larger bandwidth. So Channel bonding, what it does is it can bond multiple 20 megahertz channel to form 20, 40, 80 or 160 megahertz channel. And there's a hierarchy of channels. So one of the 20 megahertz channel is always referred to as the primary channel, and which is used for transmitting control information management frames such as beacons to the associated clients and so on. Whereas the remaining secondary channels are always used for data application. So no control information is sent over the secondary channels. Next, this frame aggregation, which is basically done for amortizing the channel access delay over larger frame size so that you can increase the efficiency of the MAC protocol. And then there's MIMO, which basically can be used to increase the reliability or increase the data rate. But these are like less critical to my work. So this is something that a lot of us might be knowing about. So this is the standard channel access procedure that Wi-Fi follows. So if you have a busy medium, the transmitter senses the channel until the channel becomes idle, and then once the channel becomes idle, it waits for a particular interval of time, which is referred to as interframe spacing. That's just to prioritize different class of packets. So prioritizing beacon frames over regular data frames and so on. And then in order to prevent collisions, there is this contention procedure which is followed, where the transmitter picks a random number between 0 and contention window, and that's referred to as back-off counter. And once the back-off counter expires, you start transmissions. So this is what's done on the primary channel. So this is what's done on the 20 megahertz channel. So, but if you have a larger channel, so if you have a 40 megahertz channel or an 80 megahertz channel, then the contention the channel access mechanism on the primary and secondary channel are different. So on the primary channel, for example, you follow the regular IFS and back off that I just explained before. But on the secondary channel, the sensing is not done for most of the time. In fact, just before the back-off counter expires, just an PIFS amount of time before the back-off counter expires, the secondary channel is sensed. And if the channel is found to be idle during that period, it's considered to be available, and the transmission takes place on both the on the 40 megahertz channel here. But if the secondary channel is occupied, in that case, it assumes that the secondary channel is not available. And what it does after, if it finds a secondary channel available, depends on the particular implementation of the 802.11 AC standard. So a lot of devices use what's called as a static channel access mechanism, where if the secondary channel is found to be busy, then it waits until all the secondary channels are idle, and then it uses the 80 megahertz channel to transmit the frame. So obviously, in even even in moderate traffic conditions, this could result into very poor performance, because you want all the channels to be idle. So there are better implementations of this, wherein if the secondary channels are sensed to be idle, you just transmit on the primary channel or whatever secondary channels are available. So for example, here you find these two channels are, if one of these channels is busy, so you club these two channels to form a 40 megahertz frame. And if all channels are busy, you just regularly use the 80 megahertz channel as is. So getting back to the spectrum sharing problem. So this is what the channelization in the new band would look like. So there are, as I said, there are 7 DSRC channels that are pointed out in red, and the blue channels are the Wi-Fi channels that would that would come up if this spectrum sharing scenario would be allowed by the FCC. So you see, like channel 173, 177 and 181 here are the 320 megahertz channel that would overlap with DSRC, and then there is a 40 megahertz channel that can overlap with DSRC, and then there's an 80 megahertz channel that can overlap with DSRC. So it looks like if you enable this, if you allow Wi-Fi devices to operate in this channel, you can significantly improve the Wi-Fi performance by using larger bandwidth channels. So this is what we examine in detail in our work. So the major issue that we try to solve in this work is what's called as the priority reversal problem. So as per the rules of dynamic spectrum sharing, the primary user must always get access to the channel if it has a packet to transmit. But it turns out the channel access parameters of 802.11p, which is DSRC, and 802.11ac, which is Wi-Fi, are designed in such a manner that if the two devices have a packet to transmit, then most likely it's Wi-Fi that will get access to the channel. So this is what we don't want. So there have been a lot of proposals regarding how to mitigate this problem. So since the Wi-Fi devices get priority in access to the channel, this is often referred to as priority reversal, and this is what I'll be focusing on. And then there is of course the hidden node problem, which exists in any distributed protocol for channel access. So some of the related work that's out there, so the stakeholders from vehicular-to-vehicular communications and Wi-Fi industry came up to form what's called as DSRC Coexistence Tiger Team. I don't know why the name, but they had several meetings and they came up with two specific proposals. So one of the proposal was that if a Wi-Fi device detects the detects that a DSRC device is occupying the channel, it backs off for 10 seconds. So they came up with an arbitrary number to make it safe enough that it should back off for 10 seconds. And in order to be capable of detecting DSRC frames, it was expected to sense the 10 megahertz preambles, which is not done in the current standard. So of course this proposal was criticized because 10 seconds is too much of a time, and in any practical scenario you would expect at least one DSRC device, one vehicle to show up within 10 seconds. So every time there's a vehicle, you back off for 10 seconds. So I mean, why would Wi-Fi devices even want to transmit in that channel? So a second proposal came up and it suggested like restructuring of the DSRC channels. So what it said was you can divide the DSRC applications into two classes. So one is safety critical, and then there is non-safety critical. So you move the safety critical applications to the upper portion of the spectrum where you don't allow any sharing. So DSRC devices have exclusive use of this spectrum, but the non-safety critical applications can still be shared. So there were some criticisms to this proposal as well, but this is the more widely accepted one. And then there have been some proposals in the research community which target this issue. So this paper here, basically what it suggests is that instead of backing off for like 10 seconds, which is like very extremely conservative and prohibitively large, why not like play around with the interframe spacing aspect of it? So you can prioritize different classes of channels, different classes of traffic by modifying the IFS. So why not just modify the IFS of Wi-Fi devices when they share the spectrum? And then to mitigate the hidden node problem, you can always like make the Wi-Fi devices sense for like deeper and deeper, so that you can try to get rid of like at least reduce the hidden node problems. So these were the proposals suggested, and then there were some experiments that were carried out which showed that increasing the AIFS, which is what's used as the interframe spacing for data traffic in 802.11ac, does alleviate the priority reversal problem a little bit. So here is the contribution of our work. So we first and foremost show that, so earlier I showed a slide where I showed all the channelization options that were possible for Wi-Fi devices if it were to operate in the shared spectrum. But through our experiments, we show that at least as far as the current 802.11 AC standard is concerned, not all of these channelizations are possible. In the sense that if these channels were to if devices were to operate in these channelizations, then you cannot mitigate the interference that's caused to DSRC devices. So under these constraints, we propose an algorithm which is simple enough and it can be implemented readily at a Wi-Fi access point, and which seeks to maximize the Wi-Fi access point throughput. and then we evaluate the performance of this algorithm using experiments. So as far as the DSRC performance goes, we first characterize what happens when Wi-Fi devices are transmitting on the performance of DSRC devices. So this is a very simple topology that we use to evaluate what happens, and so the blue devices are Wi-Fi nodes and the red devices are DSRC nodes. They were close enough so that they were in the sensing range of one another. And this is what happens. So this is the packet error rate of DSRC devices, and this is the AIFS number. So AIFS is directly related to AIFS, and as you increase the AIFS of the Wi-Fi devices, so the priority of Wi-Fi device keeps decreasing, and what that does is it reduces the packet error rate of DSRC devices. So this is easily shown like at a AIFS of about 100, which corresponds to an AIFS of roughly 1 millisecond. So if the Wi-Fi devices were to back off for about 1 millisecond, the performance of DSRC would be like as if Wi-Fi devices were not there at all. So this is a very large number. Like 1 millisecond is really large when you talk about Wi-Fi devices and those numbers. Like you typically talk in microseconds when you're generally referring to these parameters. We examine that why this happens, because 802. And the same experiments when we repeated with 802.11a, which was the oldest Wi-Fi standard. So you can achieve the same achieve a zero packet error rate at about 25 or 30 AIFSM, which is much smaller than this number. So the reason for this is frame aggregation, because Wi-Fi devices, the current Wi-Fi devices, once they get access to the channel, they occupy the channel for a really long amount of time. So okay, fine, it may take a lot of time for it to get access to the channel initially, but once it gets access to the channel, it holds on to it for a really long time. So because of that, you have to make it really large so that it doesn't get access to the channel even once, because of which you really need a large AIFSN for proper coexistence between 802.11ac and DSRC. So here's the gist of what I just said, and this makes you think that okay, if you need to back off for such a long time anyway, do you even want to share the channel? So we'll see that in a bit. But this is what happens if DSRC devices operate in the secondary channel of Wi-Fi devices. So we use the same topology, but now DSRC devices are not operating on the primary channel, they are coexisting with the secondary channel of the Wi-Fi. So here we see that no matter what you do to the AIFSN, the performance of DSRC is bad regardless of the AIFS. Now the answer, once you examine the standard, it's fairly obvious, but it's not out there in the literature anyway. So the problem is that on the secondary channel, the channel is only sensed for PIFS interval of time right before the backoff counter on the primary channel expires. So no matter what you do to the primary channel, this problem cannot be mitigated. And so at least as far as the current standard is concerned, you cannot operate on any channelization where DSRC falls in the secondary channel of Wi-Fi. So this severely restricts. So this is the same diagram that I showed before. These are the DSRC channels, and these are the channels that are fine. Like Wi-Fi devices can indeed operate on these channels, sharing with DSRC. But this channel, for example, if this is a 40 megahertz channel, one of them has to be a secondary channel, but DSRC devices would overlap with the secondary channel, and if this channel is used by a Wi-Fi transmitter, then it will severely impact the DSRC operations. So you cannot use this channel, and the same logic follows for these channels and for the 80 megahertz channel. So despite having so many channels, you cannot use most of the high bandwidth channels. So this makes an even stronger case that Wi-Fi devices may not be able to operate in the shared spectrum very with any beneficial use for themselves. So to overcome this problem, what we do is we implement a simple real-time channelization algorithm which maximizes the Wi-Fi throughput under these constraints. So of course DSRC must be protected. That's the primary goal. And when the access point shares the channel with DSRC devices, the AIFS must be sufficiently high. So this is just to protect the DSRC transmissions. So in our work, we assume that when on the shared channel, it uses an AIFS of 100, which is what we saw through experiments before. And if it's not sharing any channel, then it can operate on with the regular AIFS, which is 2. So so the idea is that Wi-Fi devices are CSMA based. So every time you access the channel, you always sense the channel. So you have that information available somewhere in the device. So a lot of this information can actually be used and leveraged to take intelligent decisions at the access point, instead of like just naively selecting one channel and sticking onto that channel for a long time. So so some of the Wi-Fi device drivers give you access to this particular information in the ROM FFT form, and that's what we've used. So this is a plot that we saw from. So you can kind of create a spectrum analyzer using your regular Wi-Fi device. So this is one such plot that we saw within the lab itself. And once you know how many, what's the channel utilization, what the channel utilization looks like, you can calculate the spectral utilization, which is the fraction of time for which the channel is actually being used. So you sense the channel multiple times, then you calculate what fraction of the time the actual channel was busy, and then using that you can compute the expected throughput. So this is a very crude form in which is being used in some of the past work, but what this basically stands for is how much data you have received at the receiver, which depends on a bunch of factors like what's the number of aggregated frames, the length of a data packet, what fraction of the channel is actually idle, the packet reception rate, and the time that it takes to transmit. So there's a bunch of back-off this back-off time, there's this IFS, short IFS, acknowledgement time, and so on. So once you scan the channel, you get the spectral utilization, you calculate the expected throughput, and now you can easily take smart decisions at the access point. So this is what the algorithm looks like. So you first scan the channel, you compute the utilization and the expected throughput on each of the channels that the device can operate on. And once you have computed that, you simply tune to the channel which gives you a very high expected throughput, the largest amongst the one that you have computed the expected throughputs for. And then you keep transmitting on that channel until one of two things happen. If a DSRC device comes in, the AIFS is going to the AIFS of devices on the shared channel. What that will do is it'll make the devices back off for an extremely large amount of time. So the performance of DSRC devices Wi-Fi devices would drop drastically, and that can be easily seen at the access point, that the throughput has suddenly fallen. So this is what that condition does. So you want the throughput on the channel to be at least greater than or equal to beta times the expected throughput. If that falls below that throughput, then it's time to change the channel. I mean, there are some DSRC devices and you may want to operate on another DSRC channel or on a non-shared channel. And the other scenario is where you've been operating on a channel for long enough. So say for the first time when you were operating on a particular channel, all the channels were extremely busy. So you scanned the channel, you saw that this is the best channel that I can operate on. But as time progresses, some of the DSRC channels vacated, and they could potentially give you a better performance now. So after regular intervals of time, you keep scanning the channel, because scanning the channel actually does not incur a lot of performance loss. So while your transmissions are regularly going on, you can just scan different parts of the spectrum and just take a decision. So that's the other condition. So if you've been operating for a large enough time, that's Tmax, you can scan the channel once again and take that decision again. So Tmax, what we do is we just we make it a function of how much throughput you are expected to get on that channel. So for example, if you're already functioning on a channel that's really good, like that channel is expected to give you the highest throughput, which is close to the maximum possible throughput, then you don't want to incur even a little bit of overheads just scanning the channel and doing all this process. But if the current channel, the best channel, is giving you a very substandard performance, then you might want to do the scanning process over and over again and at a faster rate. So this is what the channel does, the algorithm does, and if any of these conditions are not met, it scans the channel again and keeps repeating. So we evaluated this in our test bed, where we had a bunch of DSRC devices and an interferer Wi-Fi pair that were operating in close vicinity of a Wi-Fi device which had the algorithm running on it. And this is what the performance looks like. So this is the traffic that we emulated on the respective channels. So you had these numbers here indicate the spectral utilization. So what fraction of the time the channel was being used. So these are the 4 channels that we evaluated. And so ideally, this channel, for example, is ideal for a certain amount of time. So initially, when the operation starts, you would expect that this channel is being used by the device that's running this algorithm. So this is what happens. And then it pretty much tracks the usage. So despite this having sometimes despite this having higher utilization, you could still use, say, some of these channels. That's because even though DSRC devices operate here, and even though you're using really high AIFS, if the traffic of vehicles is light, which happens in this case, so the spectral utilization is very low, so it makes sense for the Wi-Fi access point to operate in the shared channel also, despite the large AIFS. But if the shared channel, or if the shared channel is even moderately loaded, in that case it will simply tune to the non-shared channel. So the 169 here is the non-shared channel, which is not shared between DSRC and Wi-Fi devices. So if the traffic is light enough, it will always move on to, it could move on to the shared channel. So it's not completely useless.
So control information, it's like transmitted or received over channel 169.
No. So the device that was running the real-time channelization algorithm decided on the bandwidth as well as the primary channel. So the control information. So when I say channel 181, the control as well as the data traffic is sent on the same channel.
So there is no like carrier aggregation in this case?
There could be, but what happens is most of the times in heavily loaded conditions, what happens is 40 megahertz channels outperform poorly as compared to 20 megahertz channels. That's because the secondary channels could not be idle for a really long time, so you don't use them at all. So while this was enabled, it never switched to the 40 megahertz mode, always on the 20 megahertz mode. So this is how the performance of the algorithm was in comparison to different static channelization schemes. So this is the brown bar is what the RCA performs, and so this shows that, like, as opposed to any naive static allocation scheme where you don't change the channelization at all, the RCA can give you much better performance, at least as compared to the worst case, and sometimes even better as compared to the average case. So this is a function of time interval t, which is the time that we use to emulate traffic. Like, for example, the traffic changes after every t intervals of time. So if t is very small, then you expect the benefits of this algorithm to be smaller as compared to when the traffic changes after really long amounts of time. So so finally, this is what we kind of experienced through our experiments and our study. So Wi-Fi devices should be able to detect DSRC transmission, because that enables that will enable you to understand that whether you're sharing the spectrum with a primary device or a secondary device, because you need not be extremely conservative if there is a secondary user out there. So when you're using a shared spectrum, if you know that there's another Wi-Fi device, then you need not be that conservative. But if you know that there's a primary device, then it makes sense to back off as soon as possible. And safety critical applications can indeed be moved to the higher bands. What that can do is, if you since no longer safety critical applications are no longer being shared, you can still use the wider bandwidth channels, and thus that's the whole purpose of allowing unlicensed devices in this 5.9 GHz band. And then finally, you can modify the channel access mechanism. So instead of secondary channel sensing, secondary channels being sensed only for PIFS interval of time, you can make them go through the regular contention process where there is DIFS and when there is back off, so that you don't take the secondary channels, you don't sense the secondary channels in an unfair manner as compared to the primary channels. So that's all.